tell most of my students that chapter 8 is sort of like second part of chapter 7. So it could be incorporated as part of chapter 7, and it's a little bit shorter chapter. In chapter 8, we're going to talk a little bit more detail about what conservative versus non-conservative forces are. We mentioned about them earlier in chapter 7, and we'll also talk about potential energy. Remember back in chapter 7 when we talked about conservative forces, we gave an example something like this. We said if a force, then I made up a certain force like, and then I made up another force where I switched the y and x. Remember that example that we did where we switched the x and the y, and we said that this force has its x component is dependent only on the x variable, and this one, the y component of the force, is only dependent on the y variable. And we noticed that for this force, the left one, that the work done didn't depend on the path that the particle took, right? So that's the first thing we saw. So this one is, we said, was an example of a conservative force, right? That's the definition. So, well, the first thing we saw that the work done by a conservative force is path independent. And the way that you can tell that it is a conservative force is that the x component only is dependent on x, and y component is only dependent on y. So fx is a function of only x, and fy, the y component of y, is a function of only y. Okay? This one was an example of a non-conservative force. Okay, so its characteristic is that the work done by a non-conservative force is path dependent. So when we did the integral of the work, we needed to use the path that the particle took. Therefore, the way to tell that it is non-conservative is that the x component of the force has a y dependence. Or it could also have 3yx. It could also have an x and y dependence, but as long as it has a y dependence, it's non-conservative. So fx could be f of xy, it's still non-conservative, as long as it has some y dependence. And then fy has a dependence on x. Okay? If fy has a dependence on x and fx has a dependence on y, if the variables are switched, then that makes it non-conservative. The other characteristic of either of these forces is this. If a particle goes across a full path, let's say the particle starts out here and goes from this point to this point with this kind of a path, and then returns with this kind of a path to the same point. So this is point A to point B. So if I go from A to B, back to A, what's the work done by a conservative force? The work done in a closed path. Okay? Well, for a conservative force, since it doesn't care about the path that you take, the work done from A to B is equal to negative of the work done from B to A, so the total work done by a conservative force is 0. Okay? Whereas the work done by a non-conservative force is not 0 for a full closed path integral. Is not equal to 0. See? So work by non-conservative is not 0. You know what? Let me write it this way. Work by non-conservative, which equals work across the whole complete path, is not equal to 0 for a non-conservative force. For a conservative force, it is equal to 0. Okay? Then the third characteristic is a characteristic that we're going to use from calculus. In calculus, there's this theorem that is proven. Usually you learn this theorem in Calc 3. I think it's called Stokes' theorem, or I believe it is called Stokes' theorem or Green's theorem. It's the, whenever you have a function the theorem goes like this. Whenever you have a function whose closed path integral is 0, whenever you have a function whose closed path integral is 0, then that function can be represented as the derivative of another function, or plus or minus the derivative of another function. That's the theorem from calculus. The way that they write it in Calc 3 is that they say the function can be written as negative the gradient of another function. That's the more official way of writing it. Whereas plus or minus gradient, it could either be plus or minus, whereas the gradient is defined as the partial derivative of the function with respect to x I hat plus the partial derivative of the function u with y plus partial u partial z k hat. Okay? So that's the official way of writing it in 3D. The gradient means it's the derivative of u with respect to x, I hat, derivative of u with respect to y, derivative of u with respect to z. So only conservative forces are forces that can be represented as the derivative of some other function, okay, using this theorem, du dx. So back to the number 3 here, conservative forces can be represented as, now we could take either the plus option or the negative option, because calculus allows us to take either. But for physics, we're going to choose the negative option, and there's a reason for that. Negative the gradient of some other function. Whereas the non-conservative forces is not going to be able to equal the derivative of some function. So non-conservative forces is not equal to the negative gradient of another function. So non-conservative forces cannot be represented as the gradient of some function or the derivative of some function. Conservative forces can be represented as the derivative of some function. Now, what's the big deal about this? Let's try to see the meaning of this. Let's try to see what this u stands for. Okay, in calculus, it doesn't have to stand for anything, because this theorem doesn't just apply to forces, it applies to any function, right? So in calculus, they don't necessarily care about the meaning of this. But when you go to physics, we want to understand, does this u have any meaning? So let's come over here and see if it has any meaning. Let's first see what is meaning of u. In order to understand that, let's first see what the units of u are. I'm just going to write it as a simple one-dimensional derivative. What would be the units of u? And from that, we can kind of understand what u is. Okay, if this is newtons, this would be whatever the units of u are, let's say question mark, divided by units of dx, which is the units of meter, right?